As much as we'd like it if things always went according to plan, the world unfortunately doesn't work that way. It's pretty much impossible to get things perfect all the time, no matter how hard we try. You're still the same. Gosh. Another way of saying this is that we need 3 chloride anions, or negative ions, and life-giving process. Chemistry is no different. We're never really doing experiments in perfect conditions. Sometimes the measurements we take aren't exact. The amount of a substance we weigh can only tell us how much is there to a certain degree. Plus, we're humans, and we're bound to make a mistake once in a while. Even cross-contamination and disobedient cats might be some reasons a reaction won't produce exactly what we expect it to. When this happens, we need to calculate which substances are the limiting or excess reactants. That will help us find the theoretical and actual yields and calculate percent yields to compare what we do produce to what we plan to produce. Hi, I'm Will Komar, and welcome back to Study Hall Chemistry, presented by Arizona State University and Crash Course. Let's dive in. At this point in the series, we already know the general difference between theoretical and actual yield. As a refresher, theoretical yield is the amount of a product we're expecting to get out of a reaction, and actual yield is how much we really get. But we still need to know how to calculate theoretical yield because in the examples we've done so far, those numbers have already been given to us. So let's say that we've decided to start a mountain bike business. Each bike requires 2 tires and 1 lightweight frame. Written as a reaction, we'll say 2 tires plus 1 frame produces 1 bike. So we order all our parts and the wholesaler sends us something funky, like 9 tires and 7 frames. We'll need to know how many bikes we can theoretically make with what we've got. Let's walk through this with some help from test 2. We'll start by writing out our reaction and plugging in our givens. 9 tires and 7 frames becomes some mystery number of bikes. We'll need to find out how many bikes we can make for each of our reactant parts individually by using the ratio between each part and a completed bike. In our original reaction, we make 1 bike for every 2 tires. So if we have 9 tires and it takes 2 to build 1 bike, we can make 4.5 bikes. But it'd be pretty difficult to sell someone half a bike, unless they're into unicycles. No judgment here. So we can really only make 4 bikes. Next, let's calculate how many bikes we can make with our frames. It takes 1 frame to make 1 bike. So with 7 frames, we can make 7 bikes. It's great, but hold up. We're limited by how many tires we've got. A bike won't work without those, and we don't have enough to build 7 bikes. We can only make 4. That's why we need to find out how many bikes we can make with each part individually. It tells us what our limit is. So in this case, our tires are our limiting reactant, the piece that's used up first and ends the reaction. And since now we have extra frames left over, our frames become our excess reactant. This also means that 4 bikes, the amount we can feasibly make before running out of materials, is our theoretical yield. Now that we've calculated our theoretical yield, let's take this a little bit further. Maybe when we actually build the bikes, 2 of the tires have punctures and can't be used. That means our actual yield would only be 3 bikes. We can represent the relationship between what we were expecting and what we really produced by calculating the percent yield. This is done by dividing the actual yield by the theoretical yield and multiplying by 100%. That way, we can turn the ratio between what we really produce and what we could produce into a percentage, making it easier to see how efficient the reaction was. So our percent yield of the bikes we could actually build would be 3/4 times 100%, which would be 75%. In other words, we made 75% of the product we were hoping to, and we should probably order parts from a different company next time. Yields and limitations play a big role in chemical reactions. Sometimes when we measure or transfer liquids or powders between containers, some of the substances gets left behind. There's no way for us to ensure we got all of it into the reaction. Plus, any scale we use to weigh materials can only measure to a certain level of exactness. If it measures 10.3 grams, that could be 10.30, 10.28, or 10.34. With that in mind, we shouldn't expect to get 100% yield in any reaction. But like we saw with the bike example, we can calculate what we should get. And lucky for us, we can find the theoretical yield of more complex reactions using stoichiometry. Let's try out an example. Potassium dioxide, sometimes called potassium superoxide, or KO2, is a solid additive that's combined with water to generate oxygen. It's commonly used in medical breathing masks. So if a mask setup uses 0.283 moles of KO2 combined with 0.166 moles of water, let's find out how much oxygen we can theoretically produce in terms of moles. We need to take the same approach as our bike problem. Use stoichiometry to find out how much oxygen each of our reactants produces individually, and then compare those amounts to find whichever is smallest. So let's set up our first of the two calculations. We have 0.283 moles of KO2, and we need a result in moles of oxygen. A mole ratio would get us from moles of KO2 to moles of O2. From our balance equation, our coefficients tell us we have 3 moles of oxygen produced for every 4 moles of KO2. So we can use this for our mole ratio. When we write out our calculation, we need to cancel moles of KO2. So we should put our 4 moles on the bottom of our ratio with 3 moles of O2 on the top. When we calculate across and cancel units, we end up with 0.212 moles of oxygen produced by KO2. Now, we need to do the exact same calculation setup for 0.166 moles of water. At this point, we know the drill. We need a mole ratio, this time between oxygen and water, with water on the bottom so it cancels out. When we multiply and cancel units, we get 0.249 moles of oxygen produced by H2O. Now it's time to compare our results. The smaller number, 0.212 moles of oxygen, is the theoretical yield. It's the most we can make before we run out of KO2, our limiting reactant here. Of course, we should still measure the amount of oxygen actually produced to make sure it's enough to give to a patient who needs a mask with a percent yield above 92%. If our readings show we're producing 0.199 moles of O2, let's calculate our percent yield. If we remember the equation we talked about a couple minutes ago, all we need to do is divide our actual yield by theoretical yield and multiply it by 100%. In other words, 0.199 moles of oxygen over 0.212 moles of oxygen times 100%, we get 93.9% yield as our result. And since that's above the hospital standard, the mask producing enough oxygen for what we need. Unfortunately, not every chemistry scenario gives us our numbers in terms of moles. In those cases, we'll need to first convert from mass, usually in grams, to moles, and then calculate our theoretical yield. Let's roll with it and see what the calculation would look like. If we worked for an environmental regulations group examining the efficiency of fuels, we might need to find out the mass of carbon dioxide emitted during the combustion of acetylene fuel. If the reaction involves 15.2 grams of acetylene and 16.1 grams of oxygen, we can use these givens to solve for an answer. First, we'll need to figure out which reactant is our limiting reactant. Beginning with 15.2 grams of acetylene, we'll use 3 conversion factors to find out how much carbon dioxide each reactant can produce on its own. Since we need so many conversions, it might be helpful to write out the calculation and ratios with just units first, then fill in the numbers afterwards. We'll do that unit first approach here to show clearly how we get from step to step. All right, conversion factor time. We'll need a molar mass to first get us from grams to moles of acetylene. Then we need a mole ratio to get us from moles of acetylene to moles of carbon dioxide. And finally, a molar mass to get us from moles of carbon dioxide back to grams. From the periodic table, we can find the molar masses we need. From the reaction coefficients, we can also tell that it takes 2 moles of acetylene to make 4 moles of carbon dioxide gas. So we can use this for our mole ratio. Since we've set up our structure, let's populate our calculation with these numbers based on how the units are arranged. When we multiply across, our grams of acetylene cancel, and so do our moles of acetylene and moles of carbon dioxide. We're left with our answer, 51.4 grams of carbon dioxide produced by acetylene. Moving on, we'll do the same setup for our other reactants, 16.1 grams of diatomic oxygen. We still need 3 conversion factors to navigate us to the units we want. This time, though, we'll use the molar mass of oxygen. We'll also need a new mole ratio that gets us from moles of O2 to moles of CO2. From our reaction, it takes 5 moles of O2 to produce 4 moles of CO2. So we'll use that relationship as our mole ratio. Once we plug in our known numbers, we can cancel out grams of oxygen, and moles of carbon dioxide, and our result is 17.7 grams of carbon dioxide produced by oxygen. When we compare our results from each of our reactants, there's a pretty drastic difference. Oxygen produces fewer grams of carbon dioxide than acetylene does, so oxygen is our limiting reactant. And since we'd have a lot of leftover acetylene, this would be our excess reactant. This means oxygen will run out first, so our theoretical yield is 17.7 grams. And if our actual yield was revealed to be 17 grams of carbon dioxide, we could calculate our percent yield. we'd write 17 grams over our theoretical yield of 17.7 grams and then multiply it by 100%. We now know that this particular reaction yields 96% of the amount we expected. It's not too bad. Limiting and excess reactions are relevant to everything from bike shops to energy to medicine. In fact, the African-American chemist Charles Richard Drew even used the concepts of percent yield and limiting reactants in his research on blood chemistry. In the first half of the 20th century, he figured out that blood plasma, or blood with cells removed, lasts a lot longer in storage than normal blood and can still be used in transfusions. He increased the yields of blood that can be donated to save lives, providing blood donations for those who need it most during the Second World War. There's opportunities in nearly any career path to solve problems using percent yields and limiting reactants. They're also important for things like energy efficiency, acid neutralization, and pollution prevention. So at this point, we've covered how to calculate theoretical yield and identify limiting and excess reactants, but we still have got a bit more to learn. Next time, we'll continue our discussion by learning how to calculate how much is left over in reactions. See y'all there. Thanks for watching Study Hall Chemistry, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video and want to keep learning with us here in Study Hall, be sure to subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See y'all next time.